And without further ado, Keith Fiske will be presenting how to avoid angering the Postgres Elder Gods. And all right, you're all set.
Okay. All right. Thanks everybody for coming. My name is Keith Fiske. I'm a senior database engineer at Crunchy Data. Primarily work on third-party applications and stuff that have to do with Postgres. A little bit about Crunchy Data, where I work. We're an enterprise PostgreSQL support company. We do provide PostgreSQL to our clients. It's a fully 100% open sourced version of PostgreSQL. There's no lock-in or anything with any of our products to a specific version of Postgres or anything like that. We provide three primary products: Crunchy Postgres, which is just the standard Postgres itself, but we also provide high availability solutions, monitoring solutions, a hardened solution for transparent data encryption, and we also help to provide common criteria certification for Postgres. And if you work in any government environments, that might sound familiar. We also have Crunchy Postgres for Kubernetes. We maintain the Crunchy Postgres operator. And we also have Crunchy Bridge, which is a fully managed Postgres on your choice of cloud, either AWS, Azure, or Google Cloud. So the talk today are going to be talking about some things you want to avoid that I've decided to nickname the PostgreSQL Elder Gods. We'll start off talking about transaction IDs in general, and then the first god will be the Transaction ID Exhaustion, and the second god we'll talk about will be bloat. So what are transaction IDs in PostgreSQL? So it is an almost always increasing 32-bit unsigned integer value, so an approximate maximum value of 4 billion. And this is how PostgreSQL keeps track of the transaction state of transactions that are currently running, how to know if something is in the past and the future. It manages it with a system called multi-version currency control. And that's how Postgres allows multiple people to be reading and updating the same data, what seems to be the same data at the same time. And so in general, a tuple or row, which I use the term so the differentiation, a tuple is what we I typically actually call the actual full value in the database, and a row is the thing that's actually returned. So a row can actually be less than a tuple if you're only selecting a couple columns. So when I say tuple, I mean the actual physical data on disk there. So in general, tuple that has an insertion transaction ID greater than whatever the current transaction ID value is, that's considered in the future. So if you're in your current transaction state now, and somebody else goes and does something in their own transaction state, like in the future time compared to you, but they haven't committed it yet, that shouldn't be visible to you yet, so that's in the future. And a tuple with an insertion ID that's less than whatever the current transaction ID means it's in the past, and so that should be visible to you. And then a tuple that has a deletion transaction ID, and I'll show you these in the next slide so you have a better idea what I'm talking about, insertion ID and deletion ID. A deletion ID would be the opposite. If it has that, it means that if it has a deletion ID that's in the future, you should still be able to see that because it hasn't been deleted for you yet. But if that deletion ID is in the past compared to you, you shouldn't be able to see that data. So that's how Postgres kind of keeps track of all that. And you can see this yourself with any table in your database. There are hidden columns that if you do a select star, these don't show up. But if you actually type them out as I did in the select statement here, you'll get them back. This is just an example table from, I run my own Nextcloud server, so this is just a table from that. And you can see there what we have is called the xmin. This is what I meant by the insertion transaction ID, and the xmax, which is what we can also consider a deletion transaction ID. So you can see this tuple here has an xmin value of 1,300,000, something like that, but it has no xmax value. So that means that tuple should be visible to everybody that has a transaction ID higher than that 4690. And then you can see there are a few rows here that do have an X max value. So once that X max value is set, that means that that tuple has been deleted, and it shouldn't be visible to anybody that has a transaction ID higher than that at that point. There are also other columns called CMIN and CMAX. So say you're within your own transaction, how do you manage the visibility of your rows within your own transaction? You did an insert and a delete in your own transaction. There should be some visibility maintained for yourself as well. That's what those CMAX, CMIN and CMAX columns are. And just to throw another hidden column in there, there's this thing called a CTID. Doesn't really have anything to do with transactions or what we're talking about today, but it is a handy column to be aware of. It's basically just the excuse me, it's the physical location of where that row or tuple is within the pages. And what that can be useful for is if you're trying to clear up duplicate rows and you want to be able to easily, like, I want to keep one of these duplicate rows, you could do a deletion statement, and you could use the CTID column value to say delete all rows where CTID does not equal, like all of your other conditions, and then where CTID doesn't equal this value, and that will keep your one value. Or if you're just deleting one duplicate, you could delete that one CTID value to help get rid of that. It's not. There's other databases that kind of use the physical location values as like a unique ID for a row, or like some sort of long-term identification. You can't really do that in PostgreSQL because if you update the row or the table is rewritten, these CTID values do change. So you can't really use them as like a long-term unique identifier or anything like that. Transaction ID, so the transaction isolation level, I'm not going to get too deep into that. There's a link for that if you really want to get into things like that. It's like repeatable read and things like that. Those can affect visibility of rows and things like that as well. It's just a little bit deeper than I'm going to get today. But normal transaction IDs are compared to each other, actually doing a modulo arithmetic using 2 to the 32, so the 32-bit integer value. That means for every normal transaction ID, there's two. So remember, it's a 32-bit unsigned integer, so there's 4 billion possible values. But the way this works doing modulo arithmetic means that there's 2 billion transaction IDs that can be older than whatever your number is right now, and 2 billion transaction IDs that can be higher than whatever yours transaction ID is right now. So I'd say this link here. So I will provide the slides here for everybody afterwards if you need to. But I would say if you're trying to understand this whole transaction ID thing a little bit more than I'm explaining today, I'd highly recommend looking at this routine vacuuming link in the PostgreSQL docs. I think it's a really key piece of administration to try to understand if you're going to be doing the administration side of Postgres. So the other, what else do here? So yeah. So one of vacuum's jobs in Postgres is to, whenever you delete or update a row, is to mark either the old version of that row or the deleted version of that row, so that they're so that they're either visible or not visible to future transactions. So one of the things it does is it will set a there's a flag bit on every tuple in PostgreSQL. That Postgres will set when vacuum runs, and it will essentially mark that row as frozen, which means it's always in the past compared to every other compared to the current transaction ID value, and it will always be in the past. And the other thing that Postgres does, it also updates a visibility map, which I'll talk about here in a little bit, to make it easier for other transactions and stuff to look up the visibility of a row. It doesn't have to go to each individual row to see if that row is visible or not. It can just look at the visibility map of that table to see what rows are actually visible to itself. So I kept saying back here, normal transaction IDs. There are special transaction ID values, one of them being like the initial state of a table when it's first set up. But there's also this frozen transaction ID value. The value is actually 2. Old versions of Postgres, whenever you would vacuum a table and it would mark it frozen, it would actually update this xmin value to 2, so it would technically always be in the past. But now Postgres doesn't really do that too much anymore. It just kind of sets a bit to say that it's frozen or not, and then it'll know that. But if depending on the version of Postgres, if you're curious, you can kind of go in there and look at that. The thing to be aware of is PostgreSQL cannot freeze a row if it's actually being used by an active transaction. So if you have long-running transactions in your database, that can impede the efficiency of vacuum running. So this is one of the reasons you kind of want to monitor for long-running transactions in your database. Sometimes it's unavoidable, like you have a big data warehouse that you run super long transactions and stuff on. That's like you can't avoid those kind of things, but this is something to then be aware of, that you're kind of impeding Vacuum's ability and Postgres's ability to clean up old rows in that database because you have that active transaction that's holding on to those rows because it doesn't know what is going to be being done inside that transaction. It needs to leave the state of those rows as visible for whatever you're doing within that transaction state. So the fewer long-running transactions you can do, the more efficient Vacuum is going to be run inside database. And as I said, modern versions of PostgreSQL can actually check that frozen flag in the visibility map. So when Vacuum is running, it doesn't have to go to each individual page to see its frozen status. It can just look at the page level. And if all of the tuples inside that one page have been frozen, it can mark the whole page as frozen, and it can tremendously speed up Vacuum on really, really large tables. So if you have really large tables that have a lot of old data that's not getting touched anymore, it can really, really help you to make sure Vacuum is run fully at least once on that table to at least mark all of those old rows as frozen. And then it can run much more efficiently the next time because it can just look at all the visibility map and see what pages it has to go fix to mark those tuples as frozen, so it doesn't need to keep doing that anymore. So, but the question is then, so what happens after you've run billions and billions and billions of transactions and you haven't been able to, just maybe you disabled autovacuum for whatever reason, or you've just got Vacuum hasn't been able to run as efficiently as it needs to, and it hasn't been able to keep up. So the current transaction ID value keeps getting bigger and bigger and bigger and bigger. That's where we run into our first Elder God in the situation. And this is probably one of the worst situations you can run into in a lot of PostgreSQL administration, because essentially what happens is it blocks all writes to the table. It used to shut down the table. It used to shut down the database completely. It doesn't quite do that anymore. It can usually keep it running in most cases, but it can block all writes. So I picked the worst Lovecraftian God out there right now, Azathoth. So that's a picture of that one. So in addition to summoning this god and ending the universe, you've got a database on fire. So let's just work on the database for now. So as I said, the normal transaction ID space is circular. It doesn't have an endpoint. And a lot of people call this the wraparound problem in Postgres. Wraparound in and of itself isn't actually a problem. The database is eventually going to wrap around at some point. The number cannot keep going up forever. So the wraparound's not the problem. The problem is if it tries to wrap around and there's no transaction IDs left. So exhaustion is the actual problem here. So, and what happens then, so suddenly transactions that were in the past suddenly appear like they're in the future. And what it looks like is if the majority of your database has been frozen and vacuumed and all that kind of stuff, it can suddenly look like everything is just gone. It's not gone. It just doesn't look like it's there because you're in a bad situation. So what happens most of the time in modern Postgres now is you will not be able to write to the database anymore. You'll start getting errors that it's not able to obtain a new transaction ID or anything like that. The documentation for Postgres mentions having to go into single user mode. You have to shut down the entire database and start it up in the special single user mode to try to fix the situation. more modern versions of Postgres don't typically need that anymore, unless you're in a really bad situation. Sometimes it can be, but most of the time, if you're able to actually perform a vacuum on the database, then you can still fix this issue without having to shut the database down. You'll just not be able to write to the database until the vacuum itself is able to finish. So you may still want to like block all your applications and stuff from connecting to the database and trying to do anything. But usually you can get this fixed if you're able to get a vacuum to actually run in the database. Let's see. Yeah, so to avoid this, you want to make sure that it's necessary to vacuum every table that ever receives a write in every database in the entire cluster at least once every 2 billion transactions. Seems like a lot, and most of the time this is something most people are never going to run into for years. Having run a Postgres database, they'll never see it. But there are applications out there that can blast through millions of transactions in a day. And so if you're doing that, you may run into this sooner than you think. So it's a good thing to be able to keep an eye on. So even if you disable auto vacuum in Postgres, something still has to go through and vacuum the tables. You cannot not vacuum tables in Postgres. It is a requirement for administering a PostgreSQL database. So some other ways you can kind of see the state of your database? If you from this PG_database system catalog, this is just getting this is just a catalog that has a list of all the databases that are in your instance. So there is a column called dat frozen transaction ID. That is the lower bound on the unfrozen transactions IDs appearing in the database, in that database. So that's basically the oldest unvacuumed row in that database. And if you run this age function against that value, it can basically computes the given value compared to what the current transaction ID is. So that's what this txid current function gives you, the current transaction ID value. And so if you do this value minus, if you do txid current minus dat frozen ID, you get this age value. And this age value here is what you're actually trying to look for and figure out. And that's what you're monitoring for to get close to that 2 billion value when you're trying to monitor for this event. So any questions at all so far? I know I've been talking, and this is probably like a fire hose of information about a pretty deep subject in Postgres. So hopefully we'll at least be able to give you at least a way to monitor for it, and so you're at least aware of it. So didn't see any. I thought I heard a ding, but I don't see any questions anywhere. Okay, maybe there's just somebody else joining. Okay. So how does so the question people a lot of times ask, isn't there any way that Postgres itself can handle this this situation to keep it from getting to the point where the database can't be written to and stuff like that? And yes, there are things that Postgres does for itself. One of the first ones is this value, this setting in Postgres called autovacuum freeze max age. And so what happens is, so this value is by default 200 million. So it's well below the 2 billion value. So when this age value of any tuple in a given table reaches autovacuum freeze max age, Postgres will kick in what kind of been dubbed an emergency autovacuum. You'll know that it's this special autovacuum because if you look at pgstat activity and you see the autovacuum running, you'll see this special phrase, to prevent wraparound, at the end of it. So that means some tuple inside this table that's having the autovacuum run reached autovacuum freeze max age. And it's not a normal vacuum that runs in this case. It's a little bit more of an aggressive vacuum. And this will run even if you disable autovacuum in the database. So even if you turn autovacuum off to prevent you trying to shoot yourself in the foot, Postgres will still run vacuums in this case. So A normal vacuum can skip pages that don't have any dead tuples in them at all. So even if there's unfrozen IDs in them, so it can run a little bit faster. The aggressive one like actively searches all possible pages for unfrozen transaction IDs to try to be to get rid of that, to get those numbers down for the transaction ID values. Another new setting that was added in PostgreSQL 14 is even higher. So this value is at 1.6 billion. This is an even more aggressive, a little bit more aggressive of a vacuum, but it doesn't do as much as a normal vacuum. It skips this, it ignores this value called cost delay. I'll talk about that a little bit later. And it also completely skips vacuuming the indexes on a table. So it's trying to just be a little bit more aggressive on the table itself to get those XID values down. Excuse me. So as I was saying, don't rely on these two values if you have autovac disabled. The biggest reason being is if you rely on these values, what often happens is you won't have any vacuums running for a really, really long time. And then all of a sudden you'll have, and it's usually your largest tables too. All of your a bunch of your largest tables will all suddenly reach this auto vacuum freeze max age, and you'll just have like a super aggressive session of vacuuming that's going on for hours and hours or even days, because you've backlogged all of your vacuuming to happen all at one time when all of these bunch of these objects all reach this value. So you want routine, normal vacuuming to be happening. You don't want to rely on these things happening. So, and again, that's all kind of covered in that one the piece of the PostgreSQL documentation I talked about called this routine vacuuming section in the documentation. So how can you monitor for this? So one of the products we have at Crunchy and many other products out there for monitoring Postgres, and I would say if you have any solution or any monitoring solution for Postgres, you want to make sure at least one of the metrics it includes is monitoring for it'll either call it transaction ID exhaustion or it'll call it wraparound. It'll call it one of those things. You want to make sure that that metric is included somehow in your monitoring solution. This is the query that we include in PG Monitor for doing this. Looks kind of scary when you first look at it, but it's actually not too bad. It's an example of a common table expression. So we basically just have two queries building off of each other to run a third query here, all within one query. So the first one, we're just setting an arbitrary value of 2 billion as the highest transaction ID that we're dealing with. Obviously, technically, an integer is higher than that value, but we're just rounding it off at 2 billion. And then we're also getting the current value of the auto vacuum freeze max age from the system catalogs. So that's what this first section is doing here. And then the next section here is going through the PG database table, like I had back here, just looking at these values in the PG database table, and getting the current oldest transaction ID in each database in this second one. And then the last one here, and then we're getting the maximum values and doing some percentages at the end. So after real complicated query runs, it gives you these nice, easy metrics to read. So you have your current oldest transaction ID, your percentage toward the wraparound. That's the scary thing you're trying to avoid. But we also monitor for getting toward that this auto vacuum freeze max age value. So we're monitoring for both things. So, and typically what we do for our monitoring thresholds is we'll have the thresholds on this emergency vacuum to warn at 110% and do a critical at 125%. Reaching this value isn't actually a problem in Postgres for most cases, unless you have a whole bunch of tables reaching it at one time. Of course, that could be a problem, but reaching that value isn't typically the problem in Postgres, so we don't really want to alert on that. What we want to alert on is Postgres not keeping up with it. So if it gets to 100, so Postgres gets to 100 on the table, it goes and kicks off a vacuum, it's back down onto 100, down under 100% again, and we're fine. Never needed to do an alert. But if it starts creeping up above 100%, like it's not keeping up with running autovacuum, that's when we kind of want to know about that, and it'll be a problem. But the actual wraparound one, you actually do want to have that at like warn at 60%, and if you're at 75% towards wraparound, you're getting to a critical point in your database, and you really do need to act on it. So the thing in here is this bullet point right here. If you resolve the emergency vacuum alert, you will never have a wraparound alert. So if you're acting on things preemptively with this emergency auto vacuum alert, you'll never run into this elder god in Postgres, and your database will stay nice and frozen. So any questions about that so far? I know I kind of threw a lot at you there. Or anybody have any questions about the whole transaction ID, how that works in Postgres or version control or anything like that? Any questions at all? Okay. All right. So vacuuming in Postgres is a multitasking operation. So the first thing we talked about it's doing is it's going through and marking old rows as frozen, like marking it's marking the deleted rows as frozen. So Postgres knows to go through and it can reuse the old transaction IDs from those. But the other thing that vacuum is doing is it's taking the rows that are like when you delete a row and it's marked as unavailable or dead, the vacuum will go through and mark those deleted rows as available reusable space for future writes. So they're essentially just marked as empty space for future writes to be able to come and use that space again. So in Postgres, an update in Postgres is internally a delete and an insert. So when I say deleted rows, updates are considered partially deleted rows in that case. So as I said, vacuum marks the dead tuples as available space, and the term kind of in the community that's come around is this word bloat, and that's essentially the dead rows that that haven't been marked as available space yet, plus that available space is what gets termed bloat. You want to kind of keep that dead tuple value low, because that means if your dead tuple value is getting high, that means vacuum's not running efficiently on the table. So that's one you typically want to keep an eye on and not let it get too high on any table. But the available space is not a bad thing. Let's actually kind of skip ahead to the next thing here. Not all bloat is bad. So that reusable space means Postgres doesn't have to ask the operating system for more disk space to be able to write more data out. It can just go find empty space somewhere that has been marked as available and reuse that. So it's much less I/O intensive than having to request new space from disk all the time. The problem with that, with excessive bloat though, is it can cause heavier I/O. The best analogy for this is the old hard drive fragmentation issue from the past. It's not so much a big deal anymore. But basically, your data is it's not filling the data isn't filling the pages in Postgres. Your data is essentially getting spread across many pages across the database. But the smallest amount of information that Postgres can give back is a page. It's a 8 kilobyte size. So if your data is scattered around out a bunch of across many pages, you're pulling back much more data from disk than you actually need. So you want to kind of keep that. You want to keep the available space bloat to a minimum. So it looks like somebody had a question in there. So if the tables are highly volatile, is it good to set some aggressive vacuuming to those tables or change the default settings? I'll actually be talking about that in a little bit later. But yes, the answer to that question is yes. And I'll talk about how to do that a little bit later. So the answer to this here is, so you don't want to have a lot of bloat, but you don't want to be so aggressive. Like if you see like 2 or 3% bloat coming up on a table, you're aggressively going after it all the time because you're actually making you're actually causing more I/O, because every time there's a write to the table, the operating system, Postgres has to ask the operating system for the file system for more stuff. So you gotta find the balance here. But so the thing is here is you don't want to let the bloat get too bad. So you don't want to let bloat rise too bad. So how do you do that? So the old way, and still, and a lot of places or a lot of monitoring solutions still do this, and it's not a bad way to do it. It just all really depends on your situation. There are some very fancy queries. I think this is about an eighth of the size of the actual size of this query. You can see I cut it off on the bottom here. It's a very large query. And if you run this query, you'll get an instant response back from the database, because it's basically just reading the statistics that are on disk. But I had some, I'd say like 90% of the time, 95% of the time, this is pretty accurate, and it'll get you a good idea of the general state of the bloat and dead tuples and stuff of their state inside your database. But I've had this query do some wildly inaccurate estimates. Like the thing that really made me investigate this more was I deleted about 300 or 400 million rows from a table, which was probably about 75 to 80% of the table. And every time I ran this query, it said there was 0 bloat, or like 2%, which I just deleted 80% of the table. It should be showing like 80 if it's like either dead tuples. I mean, the dead tuples were showing up there, but it was still showing up as like not bloat or not available empty space or whatever like that. So I was looking around, and I found this is actually an extension or a contrib module that PostgreSQL core comes with. It's not installed by default, but it is available via the contrib modules. It's called pgstat-tuple. And it's not for bloat specifically. It's just basically, it's as it states, it's for getting tuple statistics out of a table. So there's a whole bunch more information that spits out than just what we use for bloat here. But what it has in there is it has the free space and dead tuple stats for tables and B tree indexes. It does have information about other indexes available in there, but nothing bloat related. And I honestly haven't found a way to check for bloat for things like gin and gist indexes. I don't know if it's an actual issue in them, but I don't know if there's actually out there. I haven't found a way to actually monitor for that. And so what pgstat-tuple does is it actually does a full table scan of the given table to give you 100% accurate statistics on what the actual state of that table is. So this is not an instantaneous result like the other query will give you, but it will give you the actual state of the given table. There is an approximate function that it comes with, and what that does is it gives you an accurate count of the dead tuples, but it only gives you like an estimate of the live and free space. So the approximate is usually actually pretty good enough in most cases, and it's a little bit quicker. But you can still get that. I think this last one here is, I think one of the reasons why some of these instant queries aren't accurate all the time is Postgres has a thing called the toast table, and I always forget what it stands for off the top of my head here. Oversized additional storage technique. Something like that. So basically, if a given row is larger than 8 kilobytes, so it doesn't fit in the same page as the rest of the row, or it's usually like a column. If a column's value doesn't fit within the 8K page of a table, it stores it off in another location, which is called the toast table. And a lot of these things, even this pgstat-tuple function, does not account for the toast table when you just scan the table itself. If you feed a table name into the pgstat-tuple functions, it gives you the bloat status of just the table, not the indexes, not the toast table, just that one given table. But you can feed that other stuff into it. So say you had a table with a toast table and 20 indexes. You would have to run this pgstat-tuple function 22 times. Once for the table, once for every index, and once for the toast table to actually get the full bloat state of a given table. There's a better way to do this, and I'll talk about that here shortly. But this is the way I've found for monitoring for bloat. And it's just an example of the stuff you can get out of the pgstat-tuple function. So it gives you the size of the table. So this, you can see this is just a brand new table. It's 8 kilobytes in size. That's the size of a page in Postgres. So this is a very, very small table. There's 6 rows in there. The length of the tuple, average length, I think. The tuple percent. So these are I'm sorry. So the tuple percentage is the live tuples that are in there, and that's like the length, the size of those live tuples. You can see we don't have any dead tuples in here, and you can see there's this is a good example of what would appear to be a high bloat value, right? There's 89% of this table is free space in this case, but it's because it's a 6-row table that's only 8 kilobytes in size. So you actually can't make this any smaller than it is. And so if you start alerting on something like this and aggressively vacuuming it, it would be vacuuming forever because you'd never be able to clean this up. So you want to keep an eye on, you want your bloat monitoring to make sense for your situation. The other thing I was talking about here too is we're called the free space map, or we're talking about that vacuum makes space of your old rows into free space that's available for other new rows that are coming into use. So when a new row comes in, Postgres, you don't want Postgres to have to go scanning all of the pages across the entire table to find out where a free spot is. It can use this free space map. So it's just a map in a given table of where all the empty space is. And this is another thing that vacuum does. So vacuum isn't just marking old rows as reusable space, marking rows as frozen. It's also going through and updating this free space map when you run a vacuum. So this is another reason you don't want to you want to have vacuum running on a regular basis, because your new rows coming in need to know efficiently where that free space it can put the new information is. So it's another good reason for making sure vacuum is running efficiently. And just an example, running free space map function on this table, and every row is just the block number and how much space is available inside that page and inside those blocks. So we still haven't actually gotten to how to effectively monitor for this, so we're got to be careful. Bloat's still coming. And so here's the easy way. This is a Python script that I wrote. It's called a PG bloat check. And all it's doing is essentially what I was describing PGStat you have to do with PGStat-tuple. So if you give PG bloat check an individual table to scan, it will go through and it will scan the table itself, all of the indexes, and the toast table. And it will also account for this other thing called fill factor that I'll talk about here in a second. So you can just run this script against the entire database, and it'll give you a nice report back, starting from the most wasted space to the least amount of wasted space, and how much space is wasted in each one. It'll tell you the indexes and how much space they may be taking up. If there's a toast table that's associated with it, it'll show you the bloat in the toast table versus the actual table in and of itself. If the toast table is the thing that's bloated, you still just run a vacuum on the regular table. You can't run a vacuum against the toast table, but it's reported back separately. Fill factor is another lesser known but very useful feature inside Postgres. So every time the fill factor is basically how much of a given page should Postgres use when it's writing to that page? Should it leave any space available for anything else? The default fill factor for tables is 100%. So Postgres is always going to try to fill 100% of a page with table data. An index is set to 90% because indexes are frequently updated. So you want to have if you have a little bit extra space always available on a given page, it's able to just tack those updates on into that page without having to find a new page. So what this means is if you have a table that is frequently updated, like updated a lot, it would probably be helpful if every update, it didn't have to possibly find a new page to put that data in there. And so you can set your fill factor to something like 75 or 70% on a heavily updated table. And what that will do is it will only fill up 70% of a page to leave that room for future updates and allow those updates to be quicker. Another thing that Postgres can do is if an update is able to put the next value inside the same page, Postgres can do something called a heap-only tuple update. So if there's an index associated with that column, Postgres can, it'll basically put the new value in the page and put a link from the old value to the new value, and then it doesn't have to go update the index. So it only updates the heap, it only updates the table. It doesn't have to go update the index, so you save an index right. So that's another reason for doing stuff like fill factor. You can make if it's a heavily updated table, I guess that's what I'm essentially trying to say. Go look into the fill factor feature. You might be able to get some more performance out of your database there. And the bloat check script accounts for the fill factor. It does not consider empty fill factor space to be bloat, because that's essential to the running of your database. So, and then the script also has filters. You can watch for a minimum object size. I'd say there's no reason to check a table under a gigabyte in size for bloat, because under a gigabyte in size, you're probably not going to notice much of a difference if you vacuum it or not, based on the space in there. So that's one thing you can do. And then you can also monitor for wasted space, and it's got some very, very fine-grained filtering. And then it stores the result in a table in the database. So as I said, this is not a fast scan. Like a terabyte database may take about an hour or so for this script to scan it. And so you don't want that to be your real-time monitoring on this. So you can run this in the background. Like maybe I would say you'd run this at once a month at the most, maybe once a week. You don't have to run this very often. But then your monitoring solution can then go query the results in the table. So you're not actually running the bloat scan at the time your monitoring is scraping for the metrics. It'll just query the results that are inside this table, so they'll come back instantly. So any questions about bloat or anything like that? We're going to go on to talking about vacuum tuning here next. Okay. So vacuum tuning is a solution that is for fixing both of the two problems we talked about today, both the transaction ID wraparound and bloat. Vacuuming is the solution for both of these issues. And so there's a PG settings table in the system catalog, and these are a list of settings to keep an eye on and possibly tune in the database when you're looking at trying to fix your vacuum tuning and things like that. So you can see I have the auto vacuum freeze max age in here and the value of 200 million. So that's obviously one of the things here. Auto vacuum is set to on in this case, and then we'll start talking about some of these other values here. So the other question is, when does auto vacuum run? What triggers Postgres to actually run its auto vacuum daemon? So as I said before, the auto vacuum freeze max age controls when that emergency auto vacuum runs. So that's one of the first that we already talked about. That's one of the things that will trigger a table to have a vacuum run on it. If you have a very, very busy database, I've frequently seen people increase this vacuum freeze max age up to, I'd say, like even 1 billion. It's still, 1 billion's halfway to the higher value, so that's still well below most critical thresholds. But what that does is it gives Postgres a little bit more time to just do regular vacuums. You're not kicking in that emergency auto vacuum as often as it needs to run. So you can try to increase that if you see that emergency auto vacuum running a lot. First, try to examine and make sure there's no other problems, but you may also want to increase this value. This is another thing in there, a vacuum freeze table age. There's another non-wraparound emergency vacuum that can get triggered. In that case, what is that one value? Actually, I forget what that one is. So it's another one you can look at if you need to. But these other ones here are what actually trigger normal vacuums to be kicked off. So there's these vacuum scale factor and analyze scale factor. Oops. Yes, somebody said I was sharing the slides. Yes, I will. Yeah. So this is when a percentage of a table has been updated or deleted. So this the vacuum scale factor will trigger the vacuum to go, and the analyze scale factor will actually trigger when the analyze runs. So vacuum is also what analyzes your tables to update their statistics and things like that. So you'll typically see the scale factor, the analyze scale factor is less than the vacuum scale factor because you want analyze to be running more often than your vacuum. So where's the vacuum analyze scale factor? Yes, 10. In this case, it's 10%, and our vacuum scale factor is 20%. So when 20% of the table changes, autovacuum will kick in. When 10% of the table changes, analyze will kick in. The other one, or plus another value too here. So there's also this vacuum threshold and analyze threshold. This is an actual number of tuples changing. So the other one was a percentage. This is a number. So when this number of rows changes in the table, then it kicks off the analyze or vacuum. And what actually kicks off the vacuum is if you add the scale factor plus the threshold, then the vacuum runs. So if you go back here, so when 20% of a table plus, where is it? Yeah, vacuum scale factor threshold. Yeah, so yeah, that's sorry. So when 20% of the table changes plus 50 rows, that's what triggers a vacuum. When 10% of the table plus 50 rows changes, that's what triggers the analyze. The reason for the threshold is to avoid it being super aggressive on really tiny tables. So remember my 6-row table before. If one row changed in that 6-row table and the only thing we relied on was the scale factor, it would vacuum on every single update or insert on that table. So add on 50 row changes to it. Now it only vacuums every 50 row changes or something like that. So prior to PostgreSQL 13, so you'll notice this is all talked about updates and deletes. There was nothing that would trigger an auto vacuum on an insert only table other than reaching auto vacuum freeze max age. That was the only thing that would actually trigger vacuum and analyze or vacuum on an insert only table. That was obviously a problem. So as of PostgreSQL 13, there's actually an independent values here for insert only tables or for inserts on a table. So the other thing you want to tune is your resource usage of vacuum. So how aggressive is it using your disk and your CPU and all those kinds of things. So Postgres uses a number of things together for this. So you'll see there's this vacuum cost, page dirty, page hit, page miss. So I can remember what dirty exactly is. So it's the extra I/O required to flush a dirty block out to disk. So if you go back here and look, the default value of that, I believe, is 20. Yeah, so vacuum cost page 20, 30 page. Oops. So a page hit obviously is a pretty good thing. So a page hit you see is a cost of 1, and a page miss is a cost of 2. And so what's happening is while vacuum is running and hitting the rows, it's accumulating these points. So while vacuum is running, it hits a dirty page, adds 20. It hits another one, so you're up to 21. It misses another one, so you're up to 23. So it's accumulating these values until it reaches this vacuum cost limit or auto vacuum cost limit. And when it reaches the cost limit, it pauses for cost delay time. So in this case, is auto vacuum cost delay is 2, and that's 2 milliseconds. So it's not 2 seconds, it's 2 milliseconds. So what happens is these values are accumulating, it reaches this value, it pauses for 2 milliseconds. And every time it accumulates back up to 200 again, it pauses. And so this is what auto vacuum is doing. And if you've ever noticed that a manual vacuum is faster than an auto vacuum, this is why, because manual vacuums ignore the cost delay. There is no cost delay at all when you manually go and run the vacuum command. So this is something that Postgres is doing in the background to try to not let vacuum be hogging all of your resources and stuff. But for really, really large tables, you may need to adjust these things to maybe be a little bit more aggressive. And you can do that. So you can tune these values on a per table basis. So you can go through and adjust these scale factor values and these threshold values, the auto vacuum freeze, max age, things like that, the cost delay, the cost of these things. You can all tune all of these things on a per table basis. And it's not a bad idea to do that sort of thing. You just do the alter table set command and change things like that. So common use case for doing something like this is you'll tune your database for the most common case. So these values back here are the values for the entire database as a whole. You don't want to go adjusting your scale factor down to 0.001 for the entire database. That'll be way, way too aggressive. But you may want to do that for an individual table because you want it to be more aggressive on an individual table. But a better way to do that is actually not to do the scale factor, is to actually do the threshold. And so what you can do is start analyzing your database statistics, basically run an hourly export to like a CSV with a copy command, and grab this n-tuple delete and n-tuple update values from the pgstat all tables thing for that table, and keep an eye on that for like how much of that value is changing every hour or whatever. And so then you'll know how many updates and deletes are happening on a given table. And that what you can do is set the scale factor to 0 and set the threshold value to the value to give you an idea of how often you want it to be. So say your table gets 22,000 updates a day, and then 32,000 deletes a day after you've done this analyzing. So you get about 55,000 so writes or so every day on a table. So you'd set and say you want vacuum to happen once a week, and you want analyze to happen twice a day, just to keep your stats up to date. So you could set the vacuum threshold to that 55,000 times 7 value, and then set your analyze value to that divided by 2. And if that's your average writes per day, that'll give you your vacuum and analyze running on about that schedule for you. And so how do you know if it's working? If your end dead tuple is not a relatively low number, then auto vacuum is not keeping up or running for some reason on that table. This number of rows modified since the last analyze, this number should be close to your analyze threshold value. So that value that you set back here, this should be about how many rows have been changed and since the last analyze happened. So you shouldn't see this number going much higher than what you tuned it to. For an insert only table, obviously that's what you can watch for on that one. We saw back here, there's these last vacuum, last auto vacuum, last analyze values. So the last vacuum column, this is the last manual vacuum that ran on a table, and last auto vacuum is the last time auto vacuum ran on the table. So again, also for manual analyze and auto analyze. So you want to watch for those two values. Those should be within your desired runtime interval. So if you see the last auto analyze is well over 3 days ago, but it should have been running twice a day, then you can go in and try to figure out why. And remember last time I also talked about with the fill factor and the heap only tuple update. So say you're trying to see if that fill factor is working for you, you can actually see that. This is the number of hot updates that have happened on a given table. So you'll let you know if your fill factor is actually being used effectively. So if this is not working, you want to keep your bloat under control and keep them contained. Don't let the creature out. So summarize. Transaction IDs are how PostgreSQL manages data availability. Ensure any PostgreSQL monitoring solution that you use has that exhaustion wraparound metric at some point. I will say 95, 99% of the people that we work with and tuning databases almost never run into this situation. But when you do, it's a problem. So it's a good metric to keep an eye on. At least have the alert there, so you can act on it before it's a problem. And exhaustion and bloat, as I said, there are things that are not going to happen right away. They could never happen. It could be years before there are problems. So start trying to actively monitor them now. And the more recent version of Postgres you have, the less of a problem this actually is, because vacuum has gotten tremendously more efficient over the last 5 or 6 versions of Postgres. So it's less of an issue the more recent version of Postgres that you're on. So that's it. These slides are actually available at this URL here. I can copy that and put it in chat here. But I think it'll also be available on the Meetup as well. Yeah, and also give some art credit. I really like the artwork that I found for these. And if you haven't seen Love, Death, and Robots on Netflix, that's where this Bad Creature's from. Recommend going and watching that. So, any questions?
Do we have any questions for Keith?
Thank you.
Okay, we've got comments, but it looks like we don't actually have any questions. People are saying nicely structured. Thank you, Keith. Great insights. Good stuff. Thank you.
Thank you.
Yeah, that was a great talk. Thank you so much for presenting to us.
Sure. Yeah.
Perfect. So coming up next on May 8th is What's the Opposite of a Corn Dog? Using Postgres and AI to find out with Karen Jacks. That originally had been our January talk that was rescheduled, and we're going to be having it in May. The next conference is PG Day Chicago on April 26th. After that is PGConf Dev in Vancouver, May 28th through 31st. And PGEU, October 22nd through 25th in Athens, Greece. We'll send a link by email when the video is ready, so watch our social media. And also we will, publish the link with the slides again so that everyone's got it. You can find us not only on Twitter at Bay Area Postgres, but we now have a LinkedIn account. You can search for us at Bay Area Postgres and we will come up. We do need speakers. We're always looking for speakers. Anyone who's interested, please just drop us a DM to either of our social medias, or you can contact us through Meetup. Thank you everyone for being here. This has been a really good meetup. Thank you so much again, Keith. And we hope everyone had a good time and found what they were looking for. And we will see you next time. Thank you so much.